Good afternoon and welcome everyone. I am Catherine Brookman, Associate Director, Knowledge Transfer and Exchange, and on behalf of Dr. Jack Callahan, Director of the Center of Research Expertise for the Prevention of Musculoskeletal Disorders, or CRE-MSD as we are more commonly known, we'd like to thank you for joining us today for this free webinar. We are grateful to the Ministry of Labor, Training and Skills Development for our funding, which supports the delivery of these webinars, and to our presenters who provide their expertise. We ask that you keep yourself muted for the duration of the webinar as a courtesy to the presenters and all participants. The format of today's webinar is as follows. The presentation will be given, after which time we will have 10 to 15 minutes for a question and answer period with our presenter. During the question and answer period, we ask that you type your questions into the chat box. The chat box can be pulled up on your screen by selecting the chat icon in the control panel that appears near the bottom of your screen. I will relay these questions to the presenter or a similar question should we have duplicate themes. If you have a pressing question or issue such as a technology glitch that cannot wait until the end of the presentation, please type this into the chat box and we will do our best to address it right away. This webinar will be recorded, with the recording being made available to you on our website, along with the presenter's slides shortly after today's webinar. You will also be sent a link to an evaluation. Please fill this evaluation out as it assists us in the future delivery of our webinars. Thank you so much for joining us today. And remember to watch the CRE-MSD website and the MSD prevention site for new resources and events. It is now my pleasure to introduce to you our presenter, Jack Dennerlein. Jack trained as an engineer and is a professor and interim chair in the departments of physical therapy, movement, and rehabilitation sciences at Northeastern University, and an adjunct professor of ergonomics and safety at the Harvard T.H. Chan School of Health. His research aims to prevent work-related injuries and musculoskeletal disorders through multiple research approaches that examine how the design of the environment, both built and organizational, affects worker health outcomes. His research is based on a systems approach articulated through the goal of modern ergonomics, which is to optimize system performance and human well-being. Thank you for joining us today. Jack, over to you.
Thank you, Catherine. And I imagine everybody can hear me, or else you'd let me know right away. But I want to thank you and thank the center and thank Jack for inviting me to be a participant today. I think when Jack asked me to do this presentation, I thought about technology and input devices, so that make sure that my technology is working well. Here we go. And really thinking about the fact that input devices is something I've been studying for 30 years around computer related musculoskeletal disorders and the like. And one of the things that when in working on this presentation, I always like to start off with a nice picture. And this was a stock picture actually from PowerPoint. You say insert stock pictures, and this one really like. If you notice, actually the keyboard has multiple characters on it, so it looks like it has. I'm not sure what that is, but nonetheless, it shows a nice keyboard. One of my favorite types of keyboards without the number pad to the right. It's thin. It fits on my current desk. I can move it around my plants or anything else around there. The mouse is nice and centered in the middle of the, sort of between you and the keyboard, which allows you to sort of bring your shoulders in and closer together. And so I like this picture because of that, and it shows sort of a lot of the key characteristics of input devices that I'm going to be talking about today, and really about how they matter. The other thing that this shows are a couple other things. You use the integration of mobile technology with a phone on the right, which I won't talk about today, but it is an important thing because those are not only input devices, but consumer devices, and that you consume information off of them as well. And you can't see it very well, but the old-fashioned pencil is there, but also the eyeglasses and our vision is so important to what we do in the computer. So I really like this picture a lot, and so I decided to use it. It was off the PowerPoint thing, and so it came copyright free from Microsoft. Well, I don't know if that's completely it, but it shows a lot of the key characteristics of input devices that I strongly recommend people using in terms of their devices. And the small keyboard wireless allows for a lot of flexibility in how people use it and set it up on their own workstation. So this title slide says a lot just in the photograph alone. Before I get too far along, I do want to say that I do receive funding from several industry sponsors that sell these products that I'm going to be talking about. But I do want to say that my views here are my own and represent, the research in this area for the last 30 years. And all products that I do show in here do not convert into an endorsement per se, and also that I have no other conflicts of interest to disclose in terms of that. So just getting that ethics out of there. Anyway, so for the last 30 years, like I said already, I've been studying musculoskeletal disorders and computer input devices of some sort or the other. My PhD started 31 years ago and working in the University of California, Berkeley's ergonomics program out there with David Rimple. And coming as an engineer, I was just thinking about biomechanics and thinking about the impact of that. But along came this book by Stephen Sauter and others that looked at the more of an ecological framework of injuries that sort of says it's not just the technology, but a lot of other things going on in terms of this. So so backing up a little bit into the 1990s, the RSI, the repetitive stress injury epidemic, was all the news. It was hitting the newspapers a lot because the newspaper industry all of a sudden switched from into using electronic word processors and desktop computers and the like. And so it was very prevalent and made the news a lot. And so there was a lot of issues around design of the devices. A lot of lawsuits were coming out of this, were commonplace, and everybody was blaming the computer. But over time, more and more evidence came out the issue was actually more complex than just the technology itself, and actually that it's a complex system. And while it is a complex system, still the input devices are key and fundamental to what's going on here. And I think that's the bottom line message that I want to talk about today, is that that while there's a lot of other things going on, the technology still matters, but also we have to think about the context of which it's being used in. When does it work in different contexts, and also what's the role of the individual and how does the individual play into that? So those are some of the things I want to show. By the way, I love diagrams like this, and I think I probably overuse them, but I know often when I give talks from people always say these are very academic, but what the bottom line is that it sort of has an input output and lots of feedback loops and a lot of interactions, which is really what's happening. And that's sort of the bottom line of me showing you this. So, but most of my work, my early on work, really sort of focused in on only part of this model, which is really looking at, and what we often do in the lab and when we evaluate technology around the office, it's really how does this play into the physical demands and what's the biomechanical strain? And that's sort of been a lot of the work that we've done, and sometimes looking at musculoskeletal outcomes as well. And I'll link all of that together as we move along in the presentation today. And I hope to show you, linking some of these biomechanical lessons to the epidemiology and intervention research. And I'm going to show you examples of why the technology matters and how it matters and the context of these interactions. And I'm going to wrap up with an example of how technology is going beyond biomechanics too in new ways, ways associated with augmented reality and what we've been experiencing with the COVID-19 pandemic. And as such, I think as we, this model is about 26 years old now, and it's time that we actually start thinking about new models, because I think, the technology has changed as well, and thinking about what's going on. And I don't think and maybe this is something I talked to Jack Callahan about in the CRE-MSD is thinking about how we can think about this model in a more systems approach as we move on. So moving on to this idea of biomechanical strain. There we go. Thinking about biomechanical strain, when we talk about biomechanics, in the office work, we think about posture is mainly what we all look at, whether we're a practitioner or a researcher. Posture is always there. Posture is important because it's indicators of internal loads, both and unsupported and awkward postures. These postures put mechanical loads on the tissue, which then, when they get too great or held for too long, sort of create damage and injury. Of course, we're interested in applied forces. Thinking about applied forces. Sorry, hold on a second. I want to get my laser pointer going. Here we go. So here's a picture of a lab study where we actually have a force transducer underneath the keyboard, and so we can actually measure the applied forces. That's often what we also think about. Then we have muscle activity. So what are the tissues, what's the active ingredient in the interaction with these technology? And that's often muscle activity, or what we call electromyography and EMG. This is an indication of how hard are the muscles working to do a task or do something like this. And it's part of the neuromotor control, but it's sort of the EKG of the muscles. And then also we do self-report, this nice happy picture of someone filling out a survey, asking people about what was their impressions of using the device. And it's really amazing how much, design uses this approach of self-report in developing and testing new technologies that are out there. So that's sort of the framework that I'm going to be presenting. A lot of this work is, looking at this biomechanical strain that's related to these devices. So let me give a first example of pointing devices. These are, and actually most of the time we spend on the computer is using the pointing device. Well, actually, I think more times now we actually are consuming and interacting passively with the devices. But in terms of the keyboard and the mouse, we spend about twice as much time on the mouse, using the mouse, than we do on the keyboard. Some professions, such as radiologists or videographers or people who are doing a lot of graphic design, often spend as much as 80 to 90% of their time using the mouse compared to the keyboard. So the mouse is central to functionality of what we do on the computers. And so the technology over the last 20 years, there's been a lot of different devices put out there. These are 4 classic that are out there. The traditional 2-button mouse. I'm thinking about the Windows world with two buttons. The trackball, the touchpad, which is ubiquitous on laptops nowadays as the input device and pointing device that is used in those. And then this roller bar, which actually flips the mouse upside down in many ways, and instead of moving the mouse around, you actually move the mouse pad around. You have this bar here that can rotate and also slide left and right. And that then the encoder reads that movement and translates it to the screen, to the cursor location, and also decouples the buttons from the device as well. So not only, the issue with all of these devices up here is that the buttons and the movement device are coupled together, and therefore they can't be disjointed and provide other alternative ways of doing it. You have to use the same hand that you're moving the mouse with to also activate the buttons, and that can create a stress. And so anecdotally, there's lots of folks use this device with symptomatic. When I say folks, practitioners will often recommend using this device for people who have history of carpal tunnel or tendonitis of the muscles of the wrist, or carpal tunnel syndrome related symptoms, or other tendinitises of tendons that cross the wrist and finger joints. And they have seen positive results on this. And so what we did in our lab was did a study that really sort of looked at what are sort of the biomechanical differences across using these different devices. And so we looked at EMG, we looked at self-report, and we looked at posture in terms of that. So going forth, so our idea here, we did a laboratory study where we had about 20 people, I think it was, come into the lab and use these different devices doing typical things. And so we looked first at the muscle effort, the EMG, and we see that, that the devices, there was a difference across the devices, and this roller mouse did perform better in that it had a lower EMG, lower muscle activity of the forearm muscles compared to the other devices. The mouse was second, and then these two were a little bit higher. And this was just one muscle. We saw most of the effect in the extensor muscles of the wrist. So the muscles that sort of are anti-gravity, that sort of hold the fingers up and hold the wrist up when they're interacting with these devices. We saw that people were able to relax their hand a little bit more compared to the other devices. All small, and is this small, small differences? We're talking only 7 to 8%, in terms of the differences of the values of the maximum strength that someone can actually exert with these muscles. So these are low levels already, but if they're sustained for a long period of time, a difference of 1% can make a huge difference if they're sustained for 8 hours a day, if you think about a computer user or a Zoom user. So that was our first thing. We also saw that similar with the self-report, although everybody that we had tested were consistently mouse users. They did like using the mouse, but the roller mouse did no worse, which we thought was a positive finding, whereas the trackball and the touchpad were there. But again, like I said, these were all computer users who were used to using a mouse. They weren't used to these other technologies, but the roller mouse right off the bat, they seemed to like and did quite well with that. What was most interesting to me was that, in all the years was some of the changes we saw in posture. And this was really our main hypothesis, was when we looked at people using the roller mouse, what we noticed was that their hands did seem more relaxed, their fingers were closer together, and they just seemed to, you could just see a difference in terms of how they were interacting. And I think a lot of it has to do with the decoupling of the buttons, because what you see here is that when you have a two-button mouse, you see that the fingers are spread out much larger compared to when they're using the roller mouse. So we actually measured the distance between, we had a motion analysis system measuring the finger postures, as well as the rest of the upper extremity in the arm. But we measured the distance between the index and the middle finger, as well as between the middle finger and the ring finger. And that's what the blue is the difference between the index and the middle finger. And what we see with the two-button mouse is people have to split their fingers apart. But with the roller mouse, the fingers could be together and more together and a little bit more comfortable. Holding your fingers apart requires using the intrinsic muscles, which then require firing other muscles in your forearms. It just puts an extra strain. I mean, you could just do a simple task yourself right now of, just taking your index finger and moving it away, keeping it semi-straight and just trying to hold it there for, 15 seconds. You start feeling it in your arm. You start feeling the fatigue and stuff. Or maybe I have tendonitis or something. I need to go see a PT. But anyway, the issue there is, that puts an extra strain on the finger. And in all the years that people have been studying mice, no one's actually looked at this parameter, and it was kind of surprising that no one had before. But we definitely saw that these different devices, the spread out was different. And I think it definitely shows that there's probably a load reduction for this roller type of mouse compared to the standard two-button mouse. What would be interesting is to look at an Apple mouse, which doesn't have two buttons, only has one mouse, one button, and seeing how can people pull their fingers together and is there less strain there? We didn't test that hypothesis in here, but that's something that we could definitely test out with this. Now, I talked about earlier that context matter. And so this is just looking at the devices in the hand. But, as the old saying goes, the hip bone's attached to the leg bone, which is attached to this. Well, the hand is attached to the upper arm. And then these devices actually sort of dictate a place in the workstation itself. And as a result, the different technologies which really are focusing on the hand also impact the shoulder and more proximal joints. And I think that's sort of what's kind of really fascinating about this technology, is that while it might be addressing one issue, it also is addressing other issues in terms of what it's doing for the rest of the upper extremity. So like the mouse and the trackball, for example, are always placed to the right of the keyboard. And as such, the shoulder is externally rotated. Now, in a laptop or, the mouse, or even the picture I showed you at the very beginning, the mouse was actually located between the keyboard and the person. And what that does is allow for the shoulder to be more internally rotated, putting less stress on there. The sweet spot for your hands are sort of, putting your hands together in front of you, and as opposed to having it way out where the mouse is in the left-hand parts of these pictures. And so both the trackpad and the roller mouse brought it in here. And as I said before, the roller mouse also decouples it and allows people to use the left hand. So again, sharing the both hands with the activities of the pointing device, and add some more variability to the left hand while removing some of the stuff and doing about it. Yeah. I'll talk more. Well, later on, I'll talk about the roller mouse and its wrist pads and how that sort of impacts reaching across the keyboard in terms of some of the how do you integrate these to the other things. And if it's a small, thin keyboard, I'll show you that too, and that can also help with reaching across and the roller mouse and the like. But anyway, let me move on. So the point here is saying that the context, that this technology sort of dictates a context of which matters in terms of how they are set up into the workstation and how that's going to affect other joints, not just the wrist and hand, but also thinking about the shoulder and the like. So the other aspect of this is individual factors. And something that we studied a long, long time ago was looking at differences in the genders. And one aspect of that we see is that when you look at people with wider shoulders and they're working at a keyboard and they're using the mouse, they're not as externally rotated as much as somebody with narrower shoulders and the like. And it's really fascinating because if you look at neck and shoulder disorders, there's a higher prevalence of neck and shoulder disorders among women operators, and partly this could be related to the postural effects that's different because women in general have a smaller shoulder breadth compared to men. And as a result, women have to reach more externally outward because the keyboard is one size fits all kind of idea. And the issue here is that one size fits all doesn't really work for in this situation, because what it does is add more external rotation or stress to the body for people with smaller shoulders. And so we've published this and shown this in studies and the like. But this is, again, where technology can come and save the day a little bit, and why input devices matter. And the key here is sort of thinking about this idea of getting rid of that number pad. And if you can get rid of that number pad, that can bring in the mouse closer to the center line of the body and reduce that external factor. And that could play more of a role for people who have smaller shoulders. This has been a debate about the number pad on keyboards has been something of debate for 30 years, if not more, in terms of this, because people love the number pad, so it's sometimes hard to get rid of. You'll see keyboards often being sold without the number pad, or with the number pad that can be detachable, so you can still have it, or you can have like the keyboard. This is actually a picture of my keyboard here without the number pad to the right of it, and it's one that I like a lot in that it works well. And I'll talk more about the advantages of that keyboard a little bit later on. But the idea of removing that number pad allows people to bring in the shoulder. Another approach is to move the mouse to the left-hand side, and I know lots of people who do that. The issue is, it takes time to get trained to using it on the left, and unless you're left-handed already. But the left side doesn't have that, so you can actually have the mouse closer and the like. So what I just did was, moving on, was just to getting back to our model again. I've shown the context matters in terms of this, and that it is, even if we just try to look at the technology itself, it can get complex quickly, because not only do you have the technology itself, but the technology dictates kind of the setup, and the setup really interacts with the individual, and all of that kind of plays together. And I think anybody who's practiced and gone out to work with and worked with individuals realizes that there's a lot of variability out there, and what works for some people doesn't work for everybody else. And often there's some sort of common ground that you have to find with each individual worker as you go out and try to find out what solution works for them, what equipment and what technology they have currently available. Do they love their new number pad and do they need to keep it and the like, and so those are some of the issues. So I want to move on to another example. That was the pointing device. So the other big input device is the keyboard, and the keyboard, is not going anywhere anytime soon. It's been around for, people keep asking, well, when's voice recognition and all that kind of stuff take over? We're still going to have the keyboard for a long time. It's one of the most efficient ways of entering data and information into a computer, from a human than most other ways. Our visual and other, technology is catching up, but we always end up using the keyboard to fix anything that's going on in there. So I don't think it's going away anytime soon. So keyboards come in lots of shapes, thicknesses, and also feel, or the key switch design. So we've seen these these shaped, curved keyboards. They've been around since the early 90s. In fact, Microsoft put out their first comfort keyboard in the mid 90s. I remember their ad said it fits you like an old pair of jeans. My old pair of jeans don't fit me so well anymore, but anyway, that's another story. Thicknesses, I'll talk about thicknesses in a few as well, and that thickness is really important for sort of putting, thinking about the thickness of a keyboard in terms of postures and movability. But the key switch, so I'm an engineer, so I'm diving into it. I'm diving into the how does the keyboard feel? And that is really driven by the travel and the force displacement characteristics of a key. So here's a picture of a keycap removed, and you can actually see there's a mechanism below the key that guides it. I'll describe this in a few moments, but you can actually see the scissors mechanism here and a rubber sort of dimple here that when all pressed gives it a certain feel. This is a typical sort of force displacement curve. So as you displace and travel the key, there's a certain force required to get it there, and it drops away, which gives you tactile feedback. So most keyboards have a travel, and that's really important for performance and thinking about it. But anyway, I get ahead of myself. I'm going to walk through each of these sort of slowly and walk through how the technology matters. So the shapes often affect, is often, is it trying to get folks to have straighter wrists? That's sort of the idea here, is that, relieve the wrist of awkward postures and the like. And so by using, and I demonstrate this in this picture here, that, you often using a keyboard. I remember somebody calling it like the praying mantis posture that people have in a long time. And the idea of the curved, sculpted keyboards is this idea of providing a straighter wrist in terms of that. So these shapes, there's been a lot of work that's demonstrated, in the labs, numerous studies that have shown that, yes, these in fact do create straighter wrist, and they're really important. In terms of allowing for straighter wrist, the issue is, touch typists can usually deal with this, but people who are hunt and peckers don't do so well with this, but there's fewer and fewer hunt and peckers these days as we go on. But one of the other things about keyboards is their placement. Again, getting back to this idea of, that context matters, and that is, where do we place the keyboard? And we did a study, again, a long time ago, looking at how far, if you move the keyboard away from the edge of the table, what happens to the wrist posture? And what we actually see is that the wrist actually gets straighter as you move away. You don't have to ulnar deviate as much because your elbows start coming in as you move the wrist forward. What does happen, though, is you get more flexion of the shoulder, and that can be problematic but what people do is that they start using the table or the desk in front of them more as forearm support as you move forward. And I'll explain this yellow thing in a second, because what we did see is what happens here is because they start using the forearm support, we saw less ulnar deviation of the wrist, but we saw a greater extension of the wrist until we put a wrist pad in here that sort of lifted up the arms. And that's my next slide that shows you that what happens is thick keyboards, when you have forearm support on the same surface, people start extending the wrist, and that's problematic. So what we did in this study was we saw that early on in our pilot, and we said, hey, what if we put a wrist rest here that sort of elevates and sort of levels off the playing field, if you will, of the forearm support with the keyboard. And it worked. We saw a reduction in the wrist extension. And you look at this keyboard, and it has, this big, I call them wrist obstacles as opposed to wrist pads, because they sort of force a different posture. They don't let the wrist drop below the front of the keyboard. And so I call them wrist obstacles that way. And getting back to that comment about the keyboard, that's what's really cool about the people having to reach across this to reach the keyboard. The roller mouse actually has these huge pads built into it to also, and this little roller bar is supposed to sort of fit below the keyboard, so you can actually reach across, and it's sort of in the gully in between. I don't have a picture of a laptop. Actually, I have the space to do it, but a laptop has the same thing. If you notice, the keyboard is set back away from the edge of the keyboard, mainly because it fits in the touchpad there, but also that also helps prevent that awkward wrist posture. Now, another way to do it, and why I love the thin keyboards, is that the thin keyboards also provide this way of leveling the foreground. And so the thin keyboards provide this opportunity to create straighter wrists. So these thin keyboards are out there as well as alternatives to sort of the thicker, this is actually a fairly modern, regular OEM type of mouse, the original equipment manufacturing that comes with, your desktop computer. It's a lot thinner than some of the old ones that came out in the 90s and the like, but this one is fairly thin and allows for that straighter wrist to happen. And since it's wireless, which you can see in this picture compared to the wire for this guy here, it can be moved all over the workplace and add a lot of horizontal flexibility in the workplace, adding postural variability as well, which is one of the good things. So anyway, that's sort of, thickness and forearm support around on the table plays together. So the bottom line of this kind of storyline is, this technology interacts with a larger system, and that context matters in terms of what you're doing. And so it's often these different types of technology really depends on what you're doing. This kind of big keyboard might be, is really helpful for setting the wrist, straighter, but maybe if someone's got a lot of different tasks, they want to move it out of the way. What do they do with it? That kind of stuff, where a smaller, thinner keyboard can provide you that option as well. So just lots of ways of doing, of looking at the technology and how it impacts the workers and stuff. So let me go to the key switch now. So with these thinner keyboards, we actually have to start thinking about key switch design, because what's happening is that we're starting to reduce the travel of these. And this has been happening in the laptop world for, the last 20 years as well, with the increased popularity of laptops trying to get smaller and smaller and lighter, the key travel has also had to be reduced. You think about some of the old keyboards, they're thicker than our current laptops that you get today. And so you've got a screen, you've got, when you fold up a laptop, you've got the screen, you've got the keyboard, you've got the keys, and you've got the electronics behind it, as well as all the casing in the same thickness of the old keyboard. So it's kind of really amazing in what they've had to do. So this has actually put a lot of challenges for key switch designers to really come up with different ways. And so over the years, the keyboards the travel has gone from like 3 to 4 millimeters to 1 to 2, and even now they're below 1 millimeter. And and I'm not even bringing up the soft keyboards, which have no travel, such as the touch screens on iPads and other tablets and all the smartphones. Those keys have no travel, and in fact, and as a result, they've added vibrotactile haptic feedback to give people, this idea of a switch. So when you touch your iPhone and you turn on the flashlight, for example, there's a little click feeling, and that's actually a vibrotactile feedback that's implemented electronically to give you the information that you've actually felt this switch. And so there's a lot of data out there that this tactile feedback and feeling the switch collapse and actually make contact is important in terms of performance. So as we went smaller and smaller, the challenges of providing good tactile feedback has been a challenge. And the sort of standard way that people have been doing it is this scissors mechanism here. So over here is a key switch sort of decomposed. You've got the keycap, you've got a scissors switch here that's over a rubber dimple the scissor switch sort of keeps everything level. The dimple actually collapses in a way that it sort of gets stiff, and then it gives way. Sort of has an instability in it, which gives you that feeling of like, okay, it's hard, and then poof, you've broken through the switch and done it. And then the electro contact is all below that, and that just, you can see it here, and also a side kinematic here with that. And so what we did was we did a study of the different types of travels that are out there. So here are 3 different products that have 3 different mechanisms. So here's an add-on keyboard for the iPad Pro, which has a very small travel of 0.55 millimeters. It's a dome. It's actually like a membrane, like these membrane switches, which, so this, it's sort of this is the actual mechanism pulled out here, and you can see there's a curvature to it, and you press on that dome and it sort of clips, it collapses, and that creates the contact. Around 2014-15, the MacBook Pro came out with what they call the butterfly. So instead of the scissors sort of switch here, they have a butterfly one, and this was a way of them able to get only 0.55 millimeters, so the same as this sort of membrane, very short distance, and a travel done. And here there's some videos online, you can see how it works, but it basically, these two lever arms just sort of collapse, and then they bounce back up, and you can see they sort of pivot on this point here, and then there's some elastic materials that make it bounce back and the like. And here's the scissors one here, again, 1.6 millimeters. And these are the activation forces, the forces needed to create electrical contact. So the dome's a little bit higher compared to the butterfly and the scissors over here with the travel. But you can see the dome here collapsing. It's sort of like a miniature plunger, drain plunger, for your sink. Just think about it on miniature. You sort of have that sort of ka-chunk that sort of pushes down, and that's how that works in terms of that. So what we were looking at was, how did the biomechanical strain vary with this guy? So we looked at a couple of features here, including the self-reported data, where everybody seemed to like, people did not like the short travel with the higher force and the higher kind of dimple with not much feedback. They didn't mind the shorter travel here with the butterfly, and they actually like the scissors, the larger travel. And there is some indication that larger travel is a little bit more preferred and the like. They actually also perform better with the Surface Pro. By the way, if this was strictly a video soft touch, people perform about 20% low, about a quarter to a third slower when they type on those type of keyboards compared to a mechanical feel keyboard and the like. We also looked at muscle activity, and we didn't see too much difference here, and also applied force, which really correlated with the activation force with it. This was average force, so they were only above these forces for short periods of time. That's why this force is smaller than that force. But what we saw was that, the switch design, the feel of the keyboard is important. This is something that people have been studying, again, for a while. So anyway, the keyboard matters. In terms of the shape, the thickness, and even the feel, all matter in terms of creating biomechanical strain. So let me go back to the model, and getting back to this, and actually start thinking about, let's start thinking about linking technology to the musculoskeletal disorders. So now, instead of that, let's start thinking about the musculoskeletal disorders. And this was an observational study done by Fred Geer and Michelle Marcus. That is still one of the classic ones out there. Not much research is done, but they actually looked at over 400 employees outside of Atlanta, Georgia, and they followed workers until they got either neck or shoulder pain or hand and arm, and they did a whole bunch of workplace measurements, and looked at the epidemiology of relating those metrics to having neck and shoulder pain or hand and arm pain. And what's really cool here is that this links back to some of the biomechanical strains that we saw here. Remember I said, sort of the greater shoulder flexion was actually, probably indication of using the forearm, which reduces the shoulder. And so that's a protective for neck and shoulder pain. But the other thing was for hand and arm pain, having the keyboard further away, greater than 12 centimeters away from the edge of the table, seemed protective. So both of these kind of things were put together, and some of the biomechanics that we saw before were related to this. And the other thing was having keyboard heights of greater than 3.5 centimeters above the table height. That's huge, which creates a lot, the thickness, but it sort of backs up the point that you want thinner keyboards because it really is this mechanism of the wrist and terms like this. Also, what we saw with our key switch, having smaller forces is better as well, and the like. So those were some of the things that we saw that we saw in the biomechanics that relate back to some of the epidemiology that's out there. Other ways of getting evidence of what works in terms of the technology are intervention studies. This is a mouse that actually shook when you held onto it, but you weren't moving it. So, often we just keep holding onto the mouse. So the idea of this study was, and there was a study done in Europe and one in Toronto that looked at this mouse that vibrates if you hold onto it too long. So after 10 seconds of no movement, it would vibrate and say, "Let go of me," kind of thing. And what it was doing was trying to change behaviors. And they actually saw that it reduced neck and shoulder pain and hand pain in these studies, and it was kind of interesting that this is out there. I'm not sure if it's still available to buy, but the Hoover stop was a pretty neat idea in terms of trying to change behaviors through just the technology of that. There's some other pointing devices that are out there, the trackball and these devices that are really trying to change postures in terms of this, but do they really change pain? There's some mixed evidence, meaning that this guy, there was studies that looked at this guy showed a positive effect of using a trackball, where something that's more like a joystick, these more supinated type of devices that reduce pronation and go to more supinated kind of grips don't seem to have an effect. I have a whole bunch of opinions about that, and I can tell you a long thing. This key switch does matter. This was another old study that looked at how does this force displacement curve. So this is similar to what we're used to today. This is sort of a scissors lift kind of thing. This is sort of the rubber dome that we saw on the iPad Pro. This keyboard was associated with reducing pain in symptomatic folks. This was not associated with reducing pain. So again, these things, so while we look at the biomechanics, it does link to the musculoskeletal disorders as well. And for the shapes have been, there's been mixed results on this. And I think, about the geometry of these types of different keyboards. This is an old study done in the 90s. But there's also been work looking more recently and looking at these alternative keyboards. And a lot of it, I think, depends on the context and how well do they do things. How well are they implemented, and what are some of the other things going on in the workplace. And also, we're not typing that much while the keyboard's still there, we're not typing as much as we used to in terms of that. So anyway, that's sort of, my goal was really to focus in on this idea of the biomechanical strain and the technology and stuff, but also linking it to this and demonstrating that these input devices do make a difference, definitely in biomechanical, but also in the MSK outcomes that we've been talking about as well. So with that, I sort of wanted to end with this idea of, is this really what I want to say is that, of course, these are input devices. They are part of a complex system. There's, from just an engineering point of view of movement, there are so many degrees of freedom for that expression. There's so many variables, so many things going on here. To find the perfect solution is kind of often, it's not just a solution, it's a whole set of solutions, or the solution space is quite large because there's a lot of opportunities here, and finding out what one right thing is going to solve the problem is not usually going to happen, but can get a little bit more complex in terms of that. And so that's sort of one of the things. And the other thing is, should we start thinking about this model in a little different way? And right now, you're probably all starting to suffer from Zoom fatigue. And but really thinking about the future of work and how things are changing, we're starting to thinking about, mobile devices are changing how we do things. They've been doing that for over 10 years. but now also virtual and augmented reality is coming into play. And how are these going to be being played out in the future of work? It's already been happening during the pandemic with automation, and in many ways, one of the most basic forms of of augmented reality has been Zoom. And our Zoom meetings that we've been doing, all of a sudden it's like we're kind of in a virtual augmented, conference room, but it's augmented because you're real. What you're looking at is real situations, but it's all put together. And so when we think about this model, this was a paper that I just was browsing and I found, but he really talks about some of these ideas that are in our complex model about augmented reality and how that's playing an important part in our office work, and really thinking about video conferencing technology. And he talks about all these phenomena in terming like, all of a sudden we're face to face with people that we're not used to being face to face with. And he talks about this idea of, we have an all day intensive interactions with people's faces. Whereas when we're in a one-on-one meeting, we often don't look at each other. And I sort of challenge you to think about the next time you're on a one-on-one or even in a conference room with other people, how many people aren't even looking at the speaker? And what's happening right now is you're not even looking at me talking. I'm looking at my screen, you're looking at your screen, and that takes the cognitive load and stuff. Although I keep looking at the camera because I think you're looking at me. But anyway, because I'm so used to it now. But that's part of, we're not used to doing that all the time in terms of having these big faces in our own face all the time. It's like someone's 3 feet away from you, saying, look at me. And sometimes it's multiple people. There's cognitive load that you have to think differently of the technology. You actually have technology you have to interact with. Oh, where's that mute button again? That type of stuff. And that has created a lot of stress. And of course, reduced mobility and stuff like that. So thinking about how technology has changed in the last 25 years since the solder model that was, and the Swanson model that came out 25 years ago, it's time for an update. Technology and the future of work and the pandemic have really pushed things forward in new ways that are challenging us in new ways. Not to mention, how do you give advice on what devices they should be buying? So I want to wrap up with just showing you the model again. Sort of a bottom line of what I'm talking about today is this idea of technology, people, and context, and how is that changing as we move forward, and how do we have to think about that as we deal with preventing musculoskeletal disorders of people working now in their homes and their offices and different environments, and how got to make sure they still have a comfortable mouse and a comfortable keyboard, and then all the things that are surrounding that in terms of what they're doing. So that's what I have for you, and I want to thank you. I think I went a little bit too long, but I think that was about, I think Catherine was keeping track of how many more slides I had to go. So I'm going to end there and open it up to questions.
Jack, that was absolutely perfect. Thank you so much for that thoughtful and motivating presentation. We have quite a few questions, so I'm just going to jump in and throw them out at you. Can you say something about the reach to access the keyboard when using the roller mouse?
Right, and I saw that question go up. I saw that question go up and by when we were here before, and when I was talking about that, and the issue is when you reach, can you rest the arms? And I think that's always the key aspect. Is there space to rest the forearms and sort of support that? Because when you're reaching, the issue is that you're putting a load on the shoulders to sort of lift the arms up. So the roller mouse sort of does push the keyboard away, but the roller mouse has a lot of support built into it so that you don't have to reach too far. And they've really tried to think about, can you sort of scoot up your palms on that palm rest, so that you're not extending the wrist too far. Your arms are supported and you're not pushing down. So I think it's not too much of an issue. I haven't really thought about it before I saw that question, but that's been our experience, is that, while it does push the keyboard away from you, which seems to be a good thing overall, because that also promotes more neutral postures of the wrist and prevents that. As long as the forearms can be supported, I don't think of it as being that much of an issue.
Thanks, Jack. Has there been any research on the use of the ergonomic hand shoe mouse model?
I'm not familiar with that specific mouse per se. I didn't hear the pronunciation exactly. You broke up for a second.
Hand shoe, unless I read it wrong. Hand shoe mouse.
see if I can see it in the
It's at
thing.
it's at the very beginning.
Whoops. You probably just lost my screen, didn't you? Um, there you
That's
go.
okay. We'll come back to that. I'm going to go to another question. We're noticing on some keyboards, the key sizes have been reduced. Has there been any work looking at minimum key sizes?
There is a standard, and there has been work actually a long time ago about key sizes. And there is a standard out there, the HFES ANSI 100 standard that really talks about how small you can go with keys and the distance between them. I'm not familiar with, and they're based on research that was done a long time ago, and I know that they are going to these smaller ones. Um, I find the smaller, I think there's a sweet spot. You can't go too small and you can't go too big with them because, there's, when you go too small, then people with big hands are going to start having problems. If you go too big, people with with small hands are going to be reaching too much with, stretching their fingers out and the like. So I've seen a couple presentations where people have looked at it and, at some point they get too small and people, they start, it's like the old keyboard, like typewriters, their fingers start hitting each other and it gets problematic that way. But it's more from a Fitts law performance. A lot of that research is based on performance of how big a target can it be. And when you get too small, you need to be more accurate and that adds strain.
Thanks, Jack. I'm taking my hand off my mouse as you're talking and putting it back on, which I didn't used to do. So this has been very useful. We did have some feedback on that mouse that we were asked about. Marie's indicated that the hand shoe mouse is a vertical facing mouse with the thumb being upward.
Right. Got it. So there might be some conference papers out there on that, but usually in general, what that does is, like you say, puts the thumb up, and what that does is allow for more neutral postures. But often what happens then is that you have to use more of a shoulder strategy and you lose some of the precision control, so then it might just be loading the shoulder more. So there's been mixed effects, and the data, the study, the review that I showed earlier from the Institute for Work and Health that Dwayne Van Erd did, that I was also a co-author on, shows that those really don't, while they change the posture, they sometimes can, and they change some of the forearm loading, they can add to the neck and shoulder loading. And as a result, they often don't have, when they're used a lot in the field, there's not a lot of evidence that supports them. But, I think that's, sometimes it's just the study hasn't been done that show, that really benefits them. But I think some of the issue is around motor control. Those vertical ones, you start losing that sort of fine motor control that you often need for using a mouse or a pointing device. There has been some, like Microsoft has a mouse that comes up just a little bit, and Logitech has a mouse, they don't go fully vertical. They're more sculpted mouse that allows for a little bit, not as much pronation of the wrist and of the forearm, and so they are a little, those seem to be quite promising, and are, a lot of people find them quite comfortable and use them even if they're not symptomatic. I think when we go to the more vertical mouse, those are often for people who are quite symptomatic and they just need some sort of relief.
Thanks, Jack. I use a Logitech mouse and it's great. Checking in with you if you were suggesting that static shoulder flexion is preferred over static wrist extension.
So say that again. I just need to get the logical.
Static shoulder flexion. Would this be preferred over static wrist extension?
If the forearms are supported, absolutely.
Okay, perfect.
But the forearms have to be supported. Otherwise it's, the shoulders are going to be carrying that load and that hurts. You're going to pull back. And that's really interesting because what we see is that in the seated posture, we've looked at seated versus standing postures. What we often see, and given people how do they want to set up their workstations, and what you see is when they're sitting, they often push the keyboard, flex their shoulders, and rest their arms on the table and work that way. When they stand, they bring the keyboard closer and because I think they don't get the forearm support from the table as much when they stand. As when you sit, you can sort of sort of lean back and be sort of in a recline position where all of a sudden you're well supported, both your back and all that. But when you stand, you're not as supported. And what we've seen is that people pull the keyboard closer, so you have less flow, less use of the table support for forearm support when people are standing.
Interesting. Oh,
Yeah.
thank you for
See,
that.
context matters, right?
Yeah,
That's
context matters. Hadn't thought about that.
yeah.
Jack, did the difference in the travel affect the accuracy of typing?
So, in our yes, so the problem with our study was that it was not completely fully factorial. We had combination of travel, mechanism, and force all being correlated together, so we couldn't pull that out. There has been studies that have looked at uh, at at travel, and those results I would say have been a little bit mixed, and also depends on how much travel. So there's a study out by Krista Harris at UCSF Berkeley right now at the ergonomics program out there, just a couple of years ago, where she looked at gaming keyboards who have huge travel, and but then they had it used by gamers, and they wanted they wanted some travel. They didn't want too much travel. They liked it sort of around the 2 to 3 range. They didn't want it much larger, and they were so it was kind of interesting, and it depends on what the task is around there. So for gaming, and you could go out there and buy these really mechanical keyboards. I say mechanical meaning they've got travel of 3 to 4 centimeters. They've got the old AT&T sort of keyboard clicking mechanism that's a spring, not a rubber dome and scissors, but sort of this old-fashioned kind of thing. And they're popular in the gaming. You can go on Amazon and buy them yourselves and stuff. And Logitech, I think, makes a bunch of different companies make them. But for the gaming world, they love the thick keyboards and the like. But there needs to be some travel for accuracy. What we saw in reducing from 1.5 to 0.6, we didn't see a huge decrease. It wasn't statistically significant in the keys, so we didn't see a huge loss there in our study.
Okay, that's helpful to know. Do you have any comments on adjustable keyboard trays? The individual asked this indicated that theirs adjusts on a down angle, but it doesn't adjust any other way.
Yeah, the keyboard trays, I mean, what they do is provide that angle, right? They allow your wrist to go straighter too. And in fact, for the 90s, keyboard trays were a big thing in the United States. Keyboard trays did not take off in Europe or in Australia, but they took off here in the United States. And I don't know about Canada, but I imagine it's not too different than the United States in terms of furniture sales. But it could be part of a lot of the same companies serve both. The issue with the keyboard, so the angle can allow you to get straight wrist, but there's other factors that are going on. In fact, one of the things, actually, let me see if the slide I actually showed you was this picture here. I didn't explain this, but it's user defined, right? And we went around and people had highly adjustable workstations. They had a keyboard tray where they could angle it, and they had chairs that were adjustable, and they had a keyboard height and monitor height were adjustable. And what we saw was this was the average setup that everybody had. They all had ergonomic training, and they all went positive with their keyboards instead of negative trains. And really what we saw, though, was we also did a postural study, and we realized that their elbow heights were below the keyboard, so their wrists were still straight. And so it was kind of a way of them looking at that. And the other thing is that, again, context matters. A lot of these folks, you need visual access to things. And your keyboard, while we can usually know where the alphanumeric keys are, all the other keys like Control, Alt, Function, all those type of things, and mute and the volume keys are always not in a standard location. And so we often do need to look at the keyboard. So having that visual access is important to it. So anyway, so that keyboard tray can be used to help create straighter wrists and can be really helpful in that regard. They're problematic in that they don't allow a lot of horizontal capability of movement, and often also limit where you can put your forearms and rest your forearms.
Thanks, Jack. Very, very much. We don't have time for any more questions. We might have to have you come back again. I'd like to thank all of our participants and also remind everyone that you have a chance to win one of 4 Visa $200 gift cards by participating in a Back to Work survey. You can find it on the CRE-MSD homepage under our news section. Thank you again for joining us today. And thank you so much, Jack. Enjoy the rest of the evening, everyone.
Thank you.